Morning again. Hi. So far we've heard a lot of the hardware and software and the engineering side of the Personal Space Weather Station project. But from the HamSCI perspective, one of the things that's very important is not just the engineering, but also the science that we can get from it. So the next 4 talks you're going to hear are all going to be different science use cases that are actually using amateur radio data or techniques or observations that are available today. And these things could provide some inspiration or some examples of what we might want to use the Personal Space Weather Station to do. So I'm going to start by talking about large-scale traveling ionospheric disturbances observed using amateur radio, SuperDARN, and global navigation satellite systems, so GPS, Galileo, all of those things, total electron content. And so when I did my dissertation, I was looking at medium-scale traveling ionospheric disturbances, but there's a rather broad range of what traveling ionospheric disturbances are. So TIDs are quasi-periodic variations in the F region electron density. And so medium-scale, or MSTIDs, are defined as having periods of about 15 to 60 minutes, horizontal velocities of 100 to 250 meters per second, several hundred kilometer horizontal wavelength, but less than 1,000 kilometers, and they're often from meteorological sources, we found out. So a lot of what drives the MSTIDs are disturbances from the neutral atmosphere that couple up to the ionosphere. There's also large-scale traveling ionospheric disturbances, which generally have horizontal wavelengths of greater than 1,000 kilometers. They have periods between 30 minutes to 3 hours, and these are often associated with auroral electrojet enhancements, auroral activity, and particle precipitation, charged particles coming in from space. But both of these are associated with atmospheric gravity waves that are launched by the various sources. So you get gravity waves in the neutral atmosphere that then couple in with the ionosphere and cause these variations. So MSTIDs, LSTIDs, it's traveling ionospheric disturbances. They're a type of high-frequency fading, QSB. And the reason that is if you have a transmitter over in one place, or a receiver, this is bidirectional, and you're sending a number of HF rays, say somewhere between 3 to 30 megahertz up to the ionosphere, they will get refracted back down. Now, if you have a TID coming through, this is not going to just be a smooth gradient in the horizontal direction. You're going to end up having these concavities and convex structures in the electron densities. And that's going to cause a focusing or a defocusing of the wave. So as this propagates through, you could get a focused area, which is high signal-to-noise ratio, or a defocused area, which is low signal-to-noise ratio. As that happens in time, that causes a fading. So during my dissertation, I showed this last year, I believe, I worked with these things called SuperDARN radars, which are high-frequency radar systems. Is this going to play? Maybe this won't play. All right. High-frequency radar systems that operate between 8 and 20 megahertz. So these systems actually operate in a very similar manner to ham radio HF communications. You have a transmitter located in one place. You'll launch radio waves up, and instead of having a receiver at the other end, you can have a signal array bounce back down to the ground, and then you get backscatter from the ground that goes back to the radar. And you can plot this as a function of time, and if you have these TIDs going through the radar field of view, you get these variations in signal-to-noise ratio. So the SuperDARN radars are also capable of seeing this. So my thought was, if you can see these types of disturbances in SuperDARN radars, can we also see it in the HF amateur radio data? So in this presentation, I'm now using reverse beacon network data, which is the automated system for making CW spots, fully automated, the Weak Signal Propagation Reporting Network, or WSPRnet, and we got geolocation from QRZ.com. And Bill Engelke over there, he's again the person that has done the kind favor of aggregating all of this stuff and making sure you have an appropriate geotag on each spot, and he puts that into a database. So he's provided the database from all of this. I used some observations from the Blackstone SuperDARN radar run by Virginia Tech. I used GPS total electron content from the Madrigal system run by MIT Haystack. And this is the same sort of data that they were talking about, where you can see ionospheric variations by using the two different frequencies in a received GPS signal. And then also the NASA Omni data to give me information about the geomagnetic environment at a particular time. So I started to try and find some of these signals. I started in November, and and the reason I picked that is because I knew from my dissertation that the fall and going into the winter, that's your peak MSTID season. And the reason for that is the MSTIDs I learned were associated with the formation of the polar vortex, and that happens in the fall to winter hemisphere. So you get the strong polar vortex. So that's why I looked in November. And so I looked at 1 through 5 November 2017, and here you can see some of the auroral activity. So if we focus on here, you have a peak in the auroral electrojet around 600 to 800 nanoteslas, and that's a fairly strong, what we might call a substorm. You see a peak of that on 0 UT on November 3rd. Along with that, you have a small geomagnetic storm using what's called the SIM-H index. It only goes down to about minus 30 nanoteslas. Large storms can go down to, say, minus 600 or 800 nanoteslas. And then the polar cap index, this is a measure of how much the ionospheric plasma and the magnetic field lines in the polar cap region are moving or convecting. You can derive that from there. And so there's also a peak there. So right around November 3rd, there's quite a bit of activity. So here's where I plotted the ham radio TIDs. I also need to point out, this is all of November 3rd from 2017, from 0 UT to 24 UT. Up here, we have the KP index and the SIM-H index. So it was mostly calm through the day, just a little bit at the beginning, but overall, geomagnetically, it was calm throughout the day. There were no solar flares from the GOES X-ray measurements. So that was nice and clear. Down here, I have histograms that combines both the RBN and the WSPRnet data. So this is a 2D histogram, which has 30% RBN and 71% WSPRnet data. And I'm looking at two bands, the 14 megahertz band and the 7 megahertz band. Along the x-axis, you have 24 hours in time for November 3rd, and along the y-axis, I know it's very hard to see, I apologize, you see the ground range between 500 to 2,500 kilometers. So what I can say, I see this big band of color over here. What that's telling me is that there are a lot of ham radio communications that had the midpoint of the communications right around between 1,000 to 1,500 kilometers in total distance just after 12 UT. That's what this is telling me right here. This dotted line over here, that is the solar zenith angle, so right here is local noon. So you see right away the 20-meter band is shut down at night, and this is all over just the United States, the continental United States. The 20-meter band is shut down at night, and then you have a lot of 20-meter activity during the day. Conversely, the 7 megahertz band, there's farther ranges in communication at night, which is what you expect with the lower ionization, and then you get more of the close in-range communication during the local day. Now, what's really interesting about this figure is you can see that during the day, there's this up and down motion. The ranges with which you can communicate on 20 meters, they move out and then come back in, move out and come back in, and that's over the entire continental United States. And you'll see this has a period of about 1.5 hours, roughly, between each of these. And so that is what I think is an LSTID moving through the the radio structure. You might ask, why didn't I see these sorts of things when I've made these types of plots before? I actually in order to see these, I had to reduce my bin size. So these are 2-minute by 25-kilometer bins to pull out this resolution. So you have to find a day where you have a lot of ham radio contacts going on, and to be able to make the bin size this small. It's a bit of an eye chart, but you actually, I can convince myself that there are similar structures down here as well. And in the future, I'm working with one of my students right now to try and reduce this data in such a way that you can pull those signatures out better. But it's very evident in the 20-meter band. So how about in the SuperDARN radar? This is the Blackstone radar going across the United States into Canada, and we're looking just along beam 3. And again, this is operating around 10 megahertz, and so 24 hours worth of data during the day. And this is the this is slant range away from the radar, and this is signal to noise ratio up here. And on this particular frequency, you can see they don't have much scatter at night, so you can't really get any good measurements at night from the SuperDARN radar in this mode. But during the day, you can see there's the same 3 peaks in the SuperDARN data. So there's another large-scale TID. So are we seeing this across the entire United States? Is this a localized phenomena? Is it the entire thing? We broke the United States up into 4 quadrants: the northeast, the northwest, the southeast, and the southwest, and we looked at the spots for each one. So the northeast had the best response. That's where the highest concentration of radio midpoints were. And again, you can see that the TID is strong here. In the northwest, the midpoints are more spread out. There aren't as many, but you can still see some evidence of a TID going through here. In the southeast, again, similarly, you can see the TID going through. And the southwest was definitely as you can see that as we lose spots, our data quality just drops very badly, but you can kind of see it a little bit there, much harder. So to try and understand this a little bit better and to verify that this actually is an LSTID, I called up my friend Anthea Koster. She is another scientist at the MIT Haystack Observatory, and she's responsible for this Madrigal database of GPS total electron content measurements. So this is a map of differential total electron content. This is what's derived from the dual frequency GPSs. So red means that you have higher number of electrons between the ground receiver and the GPS satellite, and blue is lower. So I'm going to play you this movie that goes between these 2 arrows, so from 15 to 18 UT, and you should look for areas of red and areas of blue coming through here. And you'll see that the radio range up here is shortest when the TEC is red or higher. So there you can see a nice coherent band of red going through. Now it's more blue, and you'll see another band of red starting to form and propagate toward the southeast. There it's going. And so the idea is the radio range is probably shortest when the TEC is red or higher, because higher electron densities is going to cause more refraction and bring your range of propagation in. Here's the next 3 hours from 18 to 21 UT. And you can see that the entire United States here has a net positive TEC. Of course, there's a lot more stuff than just this large-scale structure going on, but this is something we can absolutely pick out readily in the RBN and WSPRnet observations. And note that I didn't do any fancy processing on this. I simply looked at how many ham radio operators were spotted. Like, I wasn't using signal-to-noise ratio, I wasn't using fancy Doppler shifts, just bulk, how many people were spotted by these systems. And that's how I was able to make that figure. One thing that's interesting, here's my estimated parameters. So I took the figures I got from Anthea, and I just did a quick back-of-the-envelope estimate of the parameters and made sure they were also consistent with the RBN. So I estimated a horizontal wavelength using Google Earth of about 1,100 kilometers, so that's consistent with the LSTID. A horizontal phase velocity of about 950 kilometers per hour, a period of about 70 minutes, which is consistent with an LSTID, and a direction of travel of 135 degrees, so toward the southeast, which is also consistent with what we know about LSTIDs. We also note that the period gets progressively longer with each periodicity. So it starts off with about 1 hour, and then the next TID comes in, it's about a 2-hour period, and it keeps stretching out. So there's going to be some physics that we can pull out of there. Here's a comparison with a control day. So here, this is the November day that we were just looking at on 14 megahertz, where you can see the TID quite clearly. I had my student Diego look for some other days where you didn't see this sort of activity, and so he found a day in May where the ionosphere is almost completely flat. So you can see what the RBN and WSPRnet data looks like when you don't have TIDs going through and when you do. That's 14 megahertz. Here's 7 megahertz. So here you can see it's a little easier to see some of the TIDs going through. One of the advantages of the ham radio versus, say, SuperDARN, I really like to think of the HamSCI and the ham radio observations as really being complementary to the professional academic research systems, because SuperDARN and things like SuperDARN and the MIT Millstone Hill radar, they can provide very accurate information about the ionosphere, and they can make measurements that we can't. But we potentially can operate in modes or in places that they can't reach. So, for instance, I want to start looking at how can we see these TIDs over the oceans. There's not a lot of space physics instrumentation over there. So this is a way, and in this case, we have observations at night. SuperDARN wasn't running in a mode that had observations at night, but now using this in combination with these other instruments, we can develop a more full picture than we had before. So these are very important measurements. But yeah, here you can see some of the TIDs in the 7 megahertz on the November 3rd day, and it just is flat on in May 16th. I did look at the geomagnetic environment for the May 16th day, and I was hoping, my hypothesis was it was going to be flat, but that wasn't quite true. So there actually was a bit of auroral activity on May 16th. So you can see the auroral electrojet again is hitting between about 600 nanoteslas. So there's a few good hits there. The storm index and the polar cap index, those are more nominal, more quiet. I know this looks very jagged, but it's above 0, and it's still relatively low, 20 nanoteslas or so. And the polar cap index is only varying between, say, like -4 to 4. So I don't think this is quite as active. But I think a more rigorous analysis needs to be done before we can say for sure these TIDs we're seeing is caused by auroral activity or it's being caused by something else. But these are the things I'm looking at the moment as candidates. So in conclusion, for the November 3rd day, the geomagnetic environment, the auroral electrojet index spikes to about 700 nanoteslas at 0 and 12 UT on November 3rd. The KP index, the global K index, was less than 3. The disturbance storm time / SIM-H index was relatively quiet throughout the day, between -25 and 0 nanoteslas, and there were no X-ray flares. I'm pretty convinced that what we saw in the ham radio data is an LSTID. It has about a 1.5 hour periodicity. It appears coherent across the continental United States. It's consistent with the TID signatures we see in the Blackstone SuperDARN radar beam 13, and it's also consistent with the observations we see in the total electron content GNSS data. And we were able to estimate wavelength parameters of 1,100 kilometer horizontal wavelengths and 70-minute periods, etc. So the exact mechanism is uncertain, but I'm currently looking at auroral sources, and this shows that RBN and WSPR and similar tools can be used for monitoring LSTIDs both day and at night. So, thank you very much. Yes?
Yeah, at the very beginning you mentioned something about atmospheric gravitational waves. Did I misunderstand?
They were atmospheric gravity waves. So they're different from the gravitational waves that you hear about in, say, like astronomy. Very, very different. So atmospheric gravity waves are more related to the waves you see in the ocean. So a gravity wave is where you have a parcel of air, and it gets pushed up for some reason, it's buoyant, and then gravity pulls it back down, and then the buoyancy forces push it back up, so it causes an oscillation. Right. That's right, yes. Mm-hmm. All right. Thank you.
Because I'm a science person, I can't help but add to that little thing. Imagine winds blowing over a mountain. The parcel of air rides up as it goes over the mountain. Atmosphere gets thinner and thinner when it goes up. The oscillation has to get bigger and bigger to preserve the energy in the wave. This is like the wave coming in on the beach. Eventually, the medium is so thin that the wave can't support, the medium can't support the wave, it breaks. So you get stuff coming up, wiggle, 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 turbulence, about 90 kilometers. That launches a second set of waves, more turbulence at about 120 kilometers. And that launches a third set of waves that go into the ionosphere. The moment when Nathaniel and I go to meetings, we do not understand which waves get filtered at which altitudes. That's actually a big research topic. So when you talk about traveling ionospheric disturbances, it's one point in that wave train, and the people who do modeling tell me that that's, if you have to understand that to understand the entire energy transfer between the lower and the upper atmosphere. So putting a little bit of even extra motivation, this is a frontier research topic. People have been measuring TIDs for a long time, but not in the way that Nathaniel talked about, with that kind of coverage. It's very complementary to other things we do. Okay. 7th inning stretch, right? And if you need a break, I understand. So I'm going to follow up a little bit here, and I decided to do this in a little more tutorial measurement way, mainly because I just wanted to take you some of the thought process that I did when I wanted to understand something that's a little bit simpler than what Nathaniel is doing. And it relates to the talk that, if some of you were here yesterday, that the WA-EDU crew, specifically Christina, had mentioned, which was a simpler measurement that, for example, is one of the things that we'd like to do with a low-cost version of this personal space weather station that, again, she also mentioned, which is something called the Standards Reference Receiver, or maybe I've got that acronym wrong, but I'll talk about that in a bit. But what I just want to show you is we're all engineers here, we're all scientists, and we're all curious people. So let's be a little bit tutorial and just think about how do I just start to understand what the heck a Doppler measurement means in this case if I'm listening to WWV coming in. And what I want to show you is that it very quickly gets to the point where even if your instrument is making a very nice, accurate measurement of the Doppler shift, interpreting it is a complex thing. But that's the exciting part for people like Nathaniel and Gareth and I, is being able to dig into that and figure out what it's telling us about the ionosphere. So the talk title, and I'll have some comments in the end about some additional aspects about why this is challenging, in particular for WWV. So I'm Phil Erickson, I'm in MIT Haystack, and I've been privileged to work with the HamSCI community and with TAPR and many other people for a bit now. And cleverly, this thing has put my email address in blue so you can't read it, which is great. Look at the slides later. That way, if I make a mistake, you can't talk to me. And I have to give a lot of credit to my friend Ethan Miller, who says hello to everyone. He's in the middle of transitioning to Ohio, but he is at Johns Hopkins Applied Physics Laboratory. So K8GU has been working at HF for a very long time, including with the PserDARN radars that, for example, Nathaniel mentioned, and gave me a good amount of guidance on how to think about this problem. And again, I have to give a lot of credit to the CASE Club, David Kasdan, Christina back there, Skylar, Aiden, lots of people who are the ones that are actually going to try to make the measurements that I'm going to describe. And because I am a US taxpayer, I am extremely grateful to the National Institute of Standards and Technology for paying for WWV running for decades. And I am grateful for open source software like Python, which makes things easy. No pressure there, but you need to learn about Python if you haven't already. So this is WWV. This is a lovely QSL card you can find on the web from 1940. Someone got that nice thing, and for those of us notice that we're before Hertz, it's 5,000 kilocycles, and it was a 440 cycle wave, okay? So this is part of the National Time and Frequency Standard Dissemination. That's part of why NIST, or what used to be called the National Bureau of Standards, that's its job, right? And in fact, they've been doing this for decades, and as they're hitting the 100th anniversary of WWV this fall. And October 1st, as Christina mentioned, there's going to be a special event station, and then some of us are actually participating in a formal presentation, including the NIST director, on the 100th anniversary of WWV, and we'll try to make some arguments about whether they should continue to this, that they should continue to the 2nd century. So WWV, if you read it here, is ticking away 24 hours a day, 7 days a week. And they have certainly the transmitter complex here near Fort Collins, which is about 100 kilometers north of Denver. There's also WWVH, which is coming from Hawaii, so that's the Pacific part. And then I won't talk about WWV, but that's down at 60 kilohertz, and you know, people's watches that automatically set themselves, they're actually picking up often the VLF signal, which has got time coded on it. WWV does a whole lot more than just tick away. As you know, if you listen at the top of the minute, they will put, you know, there's even, by the way, one of the ticks will, you can, if you listen to, some of the ticks are double, tick, tick, and some of them are just once. That actually tells you what the correction time is between UT1 and the normal UTC. UT1 is the Earth time reference to the celestial reference frame. They even transmit that. And they will give you geophysical alerts, they will give you marine storm warnings, depending on where you are in the hour. They run at 2.5, 5, 10, 15, 20, and there's a 25 megahertz signal. And, you know, we're up to the 10 kilowatts of power. Some of these are 2.5 kilowatts. And the important thing for us is they're kept synchronized to the NIST time standards. So they're really nice and stable frequencies when they leave the transmitter. This is this little wonderful chart of where you are in the hour, what's happening is that you can see some of these geo-alerts happen, the marine stuff here, and you'll notice that actually during the minute they will go between 500 hertz and 600 hertz tones. That's the ones that, you know, your normal audio demodulates, you can see. But the important point is that this is AM, so this is double sideband with carrier, and the carrier is always there. And it's locked. This, if you go to the HamSCI 2019, for those of you who weren't there, if you go there, I gave a whole talk on actually looking at the ticks at the 100 hertz subcarrier and finding out that there was ionospheric signal on that. We're doing more work with that. That's not the subject of this talk, but I want to just tell you that because WWV has many features, you can also use that to do ionospheric research, separate one, but we're going to concentrate in this case on the carrier. Thank you to Rob. AI6VN, I pulled this off the web last night. This is the Kiwi SDR at KPH. And so what we have here is, there is WWV at 5 megahertz. This is 4.995 and 5.005, so this is 5 kilohertz on either side of the carrier. And I happened to click the place that said, you know, at the tone. So there it is, you know, I'll let it play while I'm doing that. And what's happening is, after they have the voice modulation, there's a 1 kilohertz tone. You can see the harmonics here at the top of the minute. And then in this case, they went to the 600 hertz pulse tone for every second. So there's the announcement. Right? And if you look, if your eyes are really good, you can see the 100 hertz BCD subcarrier in here. But the constant carrier, this constant thing that WWE is wonderful for using like 50% of its power just to keep the carrier, because that's AM for you, that's going to be our focus. By the way, this is about 60 dB on the spectrogram scale. Kiwi SDRs are wonderful. So, again, thank you, Christina. I stole this from you. My point is that the simplest thing you can do is watch the carrier and see if it's not 10 megahertz. And as she mentioned yesterday, once per second, you can just estimate the incoming frequency on some path which has to go up and somehow bounced off the ionosphere. Subtract that from what, measure it, it's 10 point whatever, subtract 10 off, report it as a Doppler shift. And then there's this, and then just the magic happens and we figure out what's happening with the ionosphere. We're going to talk about that a little bit right now. Is it that simple? How do you interpret that? So, we have to think about Doppler shift a little bit. Those of you who are thinking about the fire engine coming towards you and then away from you, and when it's coming towards you, the frequency is higher, and when it's going away, the frequency is lower. I want to have you think about that a little bit more, because you always often see pictures like this. For example, here we are, and there, you know, if you're an astronomer, all of the galaxies appear to be rushing away from you. That was Hubble. But if you're on the ground and looks like a light bulb, is perhaps an LA compact fluorescent or something. If it's moving towards you, the waves appear shorter, and it's moving away from you, the waves appear longer. Now that's most people's like Wikipedia flavor of Doppler shift, but let's think about what that really means. So, by the way, there's Bob's Volt with 200 volts DC driving a Heathkit Nixie frequency counter. Thank you, Bob. Do I get a free Volt? Talk to me later. So what's the frequency counter doing? How do we measure frequency? We're counting the number of wavefronts in a given amount of time. That's this block here. So this has got some gate on it, and it says how many times did the wavefront probably usually go through 0. And then I divide that by the time, and I get my frequency, right? Wavefronts are conserved. In our case, WWV never moves its frequency, so it's always 10 megahertz. So in a given amount of time, there's a fixed number of wavefronts that leave WWV. Now, if this were a perfect mirror and wasn't moving, the path length would always be the same, and the same number of wavefronts in the gate time would always show up. We'd measure 10 megahertz. But what if this is moving? What's happening is the path length is changing slightly. Since nothing, in this case, we're assuming this is free space, it's moving at the speed of light, those wavefronts are going to take longer to arrive if the path is longer, and so you're going to see an apparent Doppler shift. In this case, because it's moving away, the path is getting longer, it's going to appear to drop a little in frequency. So measuring a Doppler shift is measuring the change in the length of the phase path with respect to time. That's what we want to do. But it's not a mirror, right? And the ionosphere is not free space because we have these things called electrons that hang around with ions that are electrostatically bound to them, and they have a complicated structure. We're going to be much more simple than this, but what I want to just say to you is that there is some motion of this layer up and down, for example, to be very, very simple, that would mean that this path would get longer or shorter. Boy, am I going back, huh? This is Oliver Heaviside. This is the guy who figured out why these waves are refracting, which I want to remind you was a really weird problem for physicists, because if you think about it, if you think about Snell's law, total internal refraction means that the refractive index up here is less than the refractive index down here. Think about if you're underwater and you're looking up at the surface of the water, it looks like a mirror, right? Stuff is reflecting. Wait a minute. This is mostly free space. It's not really delaying that. That means that this refractive index is less than 1, so the thing's moving faster than the speed of light. That didn't make any sense. Nothing moves faster than the speed of light, right? Einstein is okay. It turns out that this guy, Edward Appleton, who got the Nobel Prize in 1947 for this work, figured out that the phase velocity can be faster than the speed of light, but the group velocity, the thing that which information travels, has to be less than the speed of light. We're interested in the phase velocity for Doppler measurements, but I just wanted to put this in perspective to make you understand that people have been thinking about this problem for a long time. Here's a nice little laser experiment. There's the atmosphere, and it's going into a less refractive index, and what does it do? It bounces. And if you go to Wikipedia, you can look at the difference between group velocity and phase velocity by basically watching the phases move here and then watching the fact that the information packet goes slower than that. So, you know, the universe is not violating classical physics. But we want to think about phase velocity, because I showed you, we want number of phase paths. How is that changing over my gate interval? So, sorry, this was done on the plane, and we had hit turbulence. So, flat Earth, folks. I'm going to start with a flat Earth. I'm going to talk with a hard reflection, free space, no ionosphere, no nothing. And here's my son is going through geometry right now. He would probably be embarrassed. So here is the phase path that we want to measure. Here's the transmitter and receiver, and we're assuming that the transmitter and receiver are not moving. This point might move. So we want R sub s, well, in this case, 2 R sub s. And the great circle distance between the transmitter and receiver and the height, remember, flat Earth. And if you go back to the 1920s, I pulled that out of Bright & Tube, 1926. There's something called the Martin equivalent phase path. Even they figured out, well, you know, if the ionosphere is bending it a little bit, it's equivalent to you measuring the path like this, even though the actual path might be like that. And that's why when you see ionograms and they talk about virtual heights, they're talking about making this assumption, even though, well, it may have done that. That's okay. We're going to measure this path from A to D to C. By the way, the Flat Earth Society has members all around the globe. You're welcome. All right. So let's do a little more math. If you just sit there and you do your little math here, you want to figure out what the change in that path is as you go through height. And if you have really good velocity, really good vision, all of this is, of course, analytic. And we want to move this thing up and down, which is dH dt. We want to move it around. And you get a very simple expression for how this path is changing as a function of time. So I should be able to work out the Doppler shift, right? By the way, there's Bright and there's Tuva. This fellow was instrumental in founding the Naval Research Laboratory. You'll see a big portrait of him if you ever go to NRL in Washington. There is the paper in 1926. And by the way, if you look at figure 9 of that paper, waveform of WWV, back when it was in Washington, D.C., this was the earliest form of an ionoson that I know about. This is actually, that little bump there is the thing bouncing off the ionosphere. So WWV shows up back in 1926. But these guys were figured out that there has to be an ionosphere, which this guy, Heaviside, had, of course, postulated. We're still hard reflection. All right, now let's be a little more sophisticated. Let's say, well, we know the Earth is round. Sorry, flat Earth people. And so this is the radius of the Earth, 6,371 kilometers. And now we have the fact that we have an H here. We're going to assume the ionosphere is circularly symmetric. It's still a mirror. Law of cosines, if you remember that. That's now this length here. Twice that is the length. It's still, you're still making somewhat of this assumption. But again, we're going to look at the change of this with respect to time. I won't show you a little more algebra, but we've gone from a flat Earth to a symmetric Earth. We're getting no more sophisticated than that. How does that work out? Well, here it is in Python. WWV at 10 megahertz as a function of takeoff angle measured from the ground. Those of you who like to do dx know you want a low takeoff angle. That would be down here. This is in degrees from 1 to 14 degrees. This is the phase path length. This is the thing that we're counting the wavefronts on. Of course, as you take off at a higher angle, the phase path gets less. The blue is the flat Earth, no ionosphere. The magenta is a circular, symmetric Earth, but no ionosphere. That's the phase path. This is its derivative with respect to time if I move the ionosphere up by about 10 meters per second. It changes about half a kilometer, depending on your model, per kilometer of motion up. And then there's the Doppler shift with my little formula right here. Doppler shifts are about 0.1 to 0.2 hertz, depending on the takeoff angle. Remember, this is going up and down. This is like 0th order, right? Okay, and the circular and the flat Earth are not that different. So here's what Christina showed yesterday. You look at the scale, the fuzz is less than a hertz. So, if I believe my circular symmetric ionosphere, maybe that's ionosphere motions in the tens of meters per second. That's very geophysically reasonable. You'll also notice that when things like sunrise happen, you can get a bump with larger motions. Some, but not all, of these interpretations are geophysically reasonable. So we're getting the right numbers even with a very simple model. I had to get my instrument in here. So if you spend a lot of money, you get a megawatt class ionospheric radar in the Republic of Massachusetts, and you use it to measure the electron density profile very precisely, and you just watch this peak go up and down. This is over about 5 hours. Ignore the blue curve and concentrate on the red one. The red one is the motion of that peak in kilometers from 190 to 240 kilometers. See this wave right here? It's one of the waves that Nathaniel was talking about. If you look at the amplitude of this wave, it's about 20 kilometers peak to peak over 75 minutes. That's 5 meters per second vertical motion. The ionosphere is very horizontally stratified. It doesn't like to move vertically. See, we're in the ballpark here. So, not bad. The interesting thing I found when doing this was, if you get more realistic, this is something called Croft and Hugasian, a radio science paper in 1968. They actually refract the thing. This is to try to figure out, and then if you love math, this is one of the few integral equations that closes analytically, and they solve it, and it's totally wrong. And Ethan and I are still trying to figure out why. Look, the sign of the Doppler shift with function to takeoff angle, it's wrong. I think the phase path derivative is not correct. So if you love to figure out why analytic equations don't close, see me after, because I have a job for you. But my point is that when you saw the data, circularly symmetric ionosphere is actually not a bad model here, at least to do the 1, 3, or 10 order of magnitude. Unfortunately, we neglected the fact that the Earth has a magnetic field and things don't propagate in the same way parallel and perpendicular to the field. So if you throw the magnetic field in there, sadly you wander off the analytically closable thing, so you use a numerical ray tracer to do that. So you could be more accurate. But hey, simple gets you pretty far. So what could possibly be wrong with this interpretation? Oh, I listed a few things. I assume the ionosphere was moving vertically. What if sometimes it's moving horizontally, and in fact it's moving a lot more horizontally than it is vertically, and I'm getting some component of that as I refract? The ionosphere is three-dimensional. Multipath. What if one ray is going like this and another ray is going just next to it, and those phase functions are coming back and confusing my counting of waveforms during my gate interval? Some of that fuzz may be in fact more than one path. In fact, it's probably pretty likely. What if the takeoff angle changes as a function of time when I'm in my gate and I'm assuming that it's constant? This is a bit of an issue that WWV and WWVH have the same carrier frequency. So if you're in the Pacific coast, like KPH, you might hear one and the other, and how are those wavefronts interfering with one another because you're just measuring a carrier frequency? Fact of life, QRM and QRN do obscure some wavefronts due to, for example, fading. This is in my backyard. This is WWV. In addition to the fact I had a frequency offset, there's fading. That's probably my neighbor turning on his LED garage light or something like that. But this is great fuel for people who do observing and who do modeling, okay? This is a challenge. Let's pull the ionosphere out of this. But it's probably not the equipment. Let's think about it. A tenth of a hertz resolution on a 10 megahertz carrier is 1 part in 10 to the 8th. John Ackerman mentioned yesterday, that's not bad. You can do that reasonably straightforwardly with existing SDRs. But that fuzz that's less than 1 hertz, I can guarantee you that there are very complex ionospheric motions in it that we don't understand. So it's a very nice problem where the data is what the data is, and then you get the modelers to try to understand it. That's how we tend to make progress in this community. So I'm really excited about even these simple measurements. I'm just going to remind you that nature is complex. This is the ionosphere over a 24-hour period. I'm going to run that again for you. Is that simple? I think not. This is a total electron content map in log scale, so the sun would be over here, nighttime would be over here. You can watch all sorts of structure in that, so it's quite complicated. So the nice thing is, think about hundreds or thousands of these Doppler receivers on WWV to some other path. And think about the fact that we're going to get all of this data that we haven't really had before because we don't do this with professional networks. especially if we fuse it with the professional information we already have that has been well calibrated because people have spent a lot of time on it. This is a very rich data set, even at this simple measure the Doppler shift for ionospheric science and space weather, so we should measure it with things like the standard software receiver that was introduced yesterday. So, just a little tutorial, just to show you that even simple things get you pretty far, and then of course the real world gets complex, but that's where the excitement is. Thank you. I'll take a question while we're setting Rob up here.
In the picture you have up here now, by the way, it was a very nice talk. Are you thinking, I mean, it lends itself to me to think that you might be able to, if you had a wide enough, diverse set of receivers, you'd get some insight into the 3D structure that you don't necessarily have access to now. Do you think that's a possibility?
Yeah, this is if you get enough ray paths, you can do tomography, for example. You can invert all of these different ray paths, which of course are counting the number of wavefronts over the entire path. But if you measure a bunch of paths that are like this and like this and like this, you can take the derivative and you can start deriving altitude information. It's opportunistic though, because the paths go where the paths go. Sadly, I don't have my knob to change the ionosphere yet. So my point is that yes, you can do some more 3D modeling, especially if you put it in a framework where you're guided by other people's data in the framework of how you model the electron density. So this is fusion. You put everything in a box and you try to make it all consistent. One more. Great.
Sorry, I'm a little confused about the physics. I've heard refraction mentioned a couple of times. It seems to me if you're refracting, you're just going to change the angle at which the radio wave eventually winds up in space. Don't you need to be reflecting? You need to be above the plasma frequency for the signal to come back?
No, actually, if you're above the plasma frequency, it does not refract. In fact, it goes transonic.
I'm sorry, that's what I meant, but below the
yeah,
plasma.
But lower, yes, you need to be below the critical frequency. And that Martin equivalent path model says that, yes, it's bending, okay? But we're going to virtually assume that it's just going up and then doing a quick turnaround and coming back. But yes, you are measuring a virtual height, not an actual one. And that's where you sometimes need other data from other systems to figure out what that actual refraction looks like. At HF, it is a problem. Things don't go in straight lines. They enter in the ionosphere and they do refract. So yeah, it's a challenge.
Yeah, I have a friend that's in Mars, and one of the things he was discussing with me on our way to Dayton this year was they are constantly scanning the HF band with their equipment to see if they've got propagation at different frequencies. And I was wondering if anybody is trying to take advantage of that data.
I don't know enough about Mars to know where that data ends up, but if Bill Engelke can grab it, we'll take it. Trust me. So if you know about that, tell Bill. We'd love it. Okay. I will yield to Rob here.
I'm here to give you some results of some investigations that we have been making into measurements of that might be relevant, hopefully relevant to the personal space weather station. In this case, we've been exploiting the use of the Kiwi SDR, which is probably most of you know, but it's a $300 retail SDR. It's a standalone unit that includes a board, a single board computer, so you talk directly to the Kiwis, and there's several thousand of these deployed and in use worldwide. So if we can well characterize the Kiwi, we thought we could utilize an extension of the software I described yesterday briefly, Whisper Daemon, which is a piece of software which is primarily so far talking to extracting whispered band signals from the Kiwis, although Whisper Daemon can be used with other receivers, and I will port it to use it with the weather station. Here is the complex of receivers that I've installed at KPH, which is a historic radio site north of San Francisco. where I'm a volunteer, and so I wore the volunteer shirt that they gave me. It's a part of the National Park Service, and this radio station is a receive-only site established ultimately by Marconi himself, and the site was identified by Dr. Beveridge in 1922, and where he put up a bunch of Beveridge antennas. We're not using those antennas anymore, sadly, but we are able to use some extraordinary antennas, TCI 530 for high-frequency reception, and exploit the incredible quietness, RF quietness of the site. So I've been working with Gwen Griffiths, G3ZIL, who has really prepared this presentation for you from data that I've acquired using this Whisper Daemon software. And we've been assisted by Glenn Elmore, who's neither of them were able to. So our attention here was to try to use the data that we can gather, the Whisper data, and to extend the data that we're using to exploit that data set, which are basically wave files. In Whisper reception, there's a 2-minute long packet cycle. And the Whisper Daemon, like the WSJTX, records a 2-minute long wave file, 12 kilosample, 16-bit wave file, and hands it off to a Whisper D utility provided by Steve Franke, which extracts the signals, the Whisper beacons that are in that 2 minutes that we're transmitting during that 2 minutes. But we realized that that in addition to that wave file contained information that was in addition to those signals. In fact, it includes a lot of information about the background noise level. So we thought we would try to extend Whisper Daemon to gather that information recorded in a global database. So we've that has been implemented since about June. We are putting the noise level data into an influx global database. We have about 20 sites with Kiwis and running Whisper Daemon from Hawaii to Moscow. So there's already a data set. There's much of work to be done. That data set needs to be, and the individual sites need to be calibrated. But we have the basic infrastructure in place to gather, record, and analyze atmospheric noise levels from across the globe. There's about half of the top Whisper stations now, top 20 stations are running Whisper Daemon, and if they choose to configure it, they can contribute that noise data. I haven't been pushing people to do it. So in this talk, I'm going to try to briefly, this is not much time, and behind all this is a 40-some page detailed report prepared by Gwen on the issues that we're summarizing here. But we wanted to, one of the things we wanted to do, of course, was to calibrate our receive system to understand to what extent we're actually measuring atmospheric noise and what other impairments were being introduced. So to that end, we did a pretty deep investigation into the Kiwi itself and the associated transmission amplification systems, antenna systems at our sites. We then wanted to look at the methodology for measuring the noise. We have this wave file. How do we extract noise level? We came up with 2 techniques for doing so, which I'll detail later in the. And then we have some examples of the results from at least 2 sites, a KPH and actually very similar site, Northern Utah Telecom has a TCI 530 at a rural site in northern Utah, and he is running Kiwis, and Clint's very well calibrated. So we have at least one other pretty well calibrated low noise site that we can, and we're showing briefly some results at the end of this talk. So one of the first things we did was to measure the frequency response of the Kiwi itself, and we were surprised to find that with a sample of 4 production Kiwis, that we were seeing a significant variation in frequency response of the Kiwi itself. There is, of course, an internal low-pass filter, 40 megahertz low-pass filter inside the Kiwi, but it turns out that measuring that filter alone, we did not see this variation. So this is actually an unexplained impairment in the Kiwi. And I don't know if this has to do with the way the signal processing is implemented by the Kiwi algorithms, but I do think the point of this is just you need to measure your system end to end. And we were surprised by the results, these results. So there's certainly, what I did do is add to the Whisper Daemon the capability to do a per band adjustment of the amplitudes so that we can compensate for this measured variation in the receive system. Looking at the sensitivity of the system, we thought it useful. We were inspired by some measurements made by Alex, I think it was, VA7OJ, took a look at the Kiwi and compared it against the Perseus, which he's kind of his reference receiver. And we were surprised and somewhat disappointed to realize that while the analytics suggest that we would have a 10 dB or so noise figure for the Kiwi, that the actual noise figure was more like 20 dB. It was terrible. And that it was originally masking the background noise that we were getting from the antenna system at KPH. So this I addressed as I think maybe needed in many receive sites by putting an external preamplifier ahead of the Kiwis. And it turns out that what I added 23 dB gain, the DX engineering implementation of the Clifton amplifier, which uses these Galley 73s. Those are, basically they have great specs, but it turns out if you take the DX engineering and put a terminator on the front of it and look at the output, there's all kinds of, the linear regulators oscillating at 100 kilohertz. So I had to go in and there's an inductor right on the output of the linear regulator inside there. So I shorted out the inductor and eliminated the oscillations. But there's, I think, a genuine need for a really good reference, low noise, high frequency and preamplifier. I couldn't find one. I mean, I'm hacking away at the DX engineering board at this stage is the best I can do. But so in addition, Adam's measurements technique suggested that we needed to look at the effect of strong signals on the signal-noise ratio. And the nonlinearities in the ADCs are, well, this is more detail on the noise factor measurements. We did two different techniques. Gwen constructed a noise generator, and Glenn constructed one, and we had pretty good calibration, and they both showed this variation. In addition to the kind of inherent this problem with the Kiwi's noise insensitivity or internal poor noise figure, we also found other sources of noise. Most specifically, the gigabit Ethernet path is a severe problem. The Kiwi itself is remarkably noise immune. I mean, you can put a 200 millivolt, 100 kilohertz square wave on the DC input and not see it in the output at all. It's amazingly immune. But once you attach cables to the Kiwi, you start seeing other sources of noise, and one of which, the one that was basically I found impossible to eliminate, was the noise associated with the Ethernet, the wired Ethernet connection. And as a result, really to get quiet results, we've had to actually make the Kiwi a wireless device. And by attaching, using a USB Wi-Fi adapter. What you see without that is you see up in, starting at about 15 megahertz, it's obvious. You see all these little lines of 64 kilohertz spacing, pairs of lines that are associated with the land stuff. So I don't know that other devices suffer from this problem, but all of the ferrites that I could stick on and the DX engineering Ethernet filters did not eliminate these the wired Ethernet as a source for these kinds of devices. So if you're building a standalone device which has many like the SDR, like the Kiwi, which has many wonderful operational characteristics, you need to pay attention to the effect of this wired Ethernet interface. I have no other examples to study in this respect, but it was basically we never found a solution for the wired Ethernet problem. Not that yes.
Is that with a terminator on the receive input, or is it hooked up to an?
I'm sorry. Was it? If you hook it up to an antenna, it doesn't make any difference. Yeah, if you put a terminator on it, you won't see anything. It's you have to realize that there's no such thing as ground. You've got the receiver here sitting in this blob, the Kiwi here, and you've got these wires going out, and the coax coming in, the SMA, and all these other devices. Yes,
And there also is shielded Cat6 cable.
Well, one of the elements of the solution is we've introduced on the SMA inputs, I have utilizing the T11 transformer from mini circuits, provides 30 dB of common mode rejection on the RF SMA input. And that does a lot to help in many situations. When you set up your SDR, it'll look great with a terminator on the input and the wired Ethernet. Stick a coax, 30-foot long coax, run it right out into your yard, put a terminator at the end of it, okay? Now take a look at what your noise looks like, okay? Well, you now have all this common mode coming in from the coax, and that ends up producing differential signals at the input of the ADC inside your SDR, and those signals appear. And that was a real the terminator helps. The T11 for a little $3 device I built 20 of them and I sprinkle them all over the place. Now, of course, they impair the the noise figure because they introduce up to a dB of loss themselves. So you don't get something for nothing in engineering. Okay, yes?
Did you see USB contributing any noise?
No, it's amazing. It turns out that if you stick a USB Wi-Fi adapter, a little dongle on the back of the Kiwi, okay, it all disappears. You don't see any noise. The thing is you get rid of all of that. Now there are other noise mechanisms that show up. The switching power supplies that I was using, which previously had been down farther in the noise level, suddenly started to appear now that the land noise went out. And then it turned out, okay, I have the ferrites on the switching noise things. And everybody says use the linear, but these devices are being battery powered, and to consume 7/12 of your battery power in linear regulators is not good when you have 8 of them. So come and see me afterwards. This is so much. Here's an example of the effect of the noise, of strong signal effect on the noise figure. What we did was we looked at we introduced a minus 14 dBm full scale sine wave off 100 kilohertz, or I guess, or 200 kilohertz off, and looked at the effect of the noise level, background noise level, in the whisper band. And you can see as you reduce that signal, the background noise level measurements go down to what you would expect. So there is a noise level modulation effect associated with strong signals present outside of the whisper band. So again, this is an effect that we hadn't really understood. It isn't so serious as it turns out. It sounds like it's a really bad thing. The absolute noise measurement levels that Adam performed, we didn't show up so well, but in practice, it turns out that isn't really a serious issue. So what kind of noise we were going to measure? There's all kinds of, there's various noise sources and characteristics of noise. So we thought we would, we wanted to focus basically on the galactic noise, atmospheric noise, and so on. But we wanted to make a measurement that that would eliminate and minimize the measurement of other sources. So we, as I described earlier, looked at we're using the WAV file as its input, and what I uncovered was that there's a sound utility that's part of Linux, SOX, sound extension utility, and one of its features is it will generate statistics on the WAV file. So what we did was we run after doing the whisper decoding, we feed that WAV file to SOX and configure it in two different ways. The first way is to look at the total RMS signal levels in 50 millisecond wide slices. In the first second, slice out of the first second of the 2 minutes, and in 8 seconds of the trailing 10 seconds. Those periods of time in the 2-minute cycle, there should be transmitters are supposed to be off. So this is a time domain slice. We're taking the noise level in periods of the whisper cycle where there should be no signals. And of course, there are signals. There are people who don't know what time it is. So you have to. What we do is we look at these and we look for the minimums and throw away the high ones and look for basically average a subset of the. So this is the histogram of the sample noise levels measured in the first second, a slice of the first second, a slice of the last 10 seconds, and then we take the minimum, and we get pretty good small distribution of sample values. And we think that this technique is a pretty useful one. The second approach was to say, okay, but this is taking 2 snapshots, still 2 snapshots in time. We would like to make a continuous measurement. So let's go take a look and look in the frequency domain. And Fox has a second statistics. It'll perform, you can tell it to do FFT on the 2-minute long sample. And if you look across it, of course, there's going to be signals there, but there are little gaps in the 200 hertz where there are no signals, because there's no transmitter. So if we take all of these, okay, and look at the lowest 30% of them, okay, across the 2 minutes, we're now getting a measurement that spans the full 2-minute cycle and gives us a second view into the noise during the 2 minutes that we found in that recording. So as you would expect, the frequencies that you most frequently select are actually off the shoulders of the whisper band. But nevertheless, because here's where you're going to find whisper signals between 1400 hertz and 1600 hertz. But nevertheless, there are times when you end up with the lowest signal levels in there. Okay. So here's the results. Here's a chart that shows the results at KPH over a 24-hour period of those levels. So as you'd expect, there's a kind of well-expected diurnal effects at the lower frequencies. And as you get up to the 30-meter band, you're starting to see, and there are variations between the 2 measurement techniques. So you can see this is the diurnal measurement, and this is the delta. In other words, how much variation there is. Anyway, what we also, because KPH is such a quiet site, we thought we would look in more detail at the noise levels being measured in the higher frequency bands. And what we seem to have identified, it appears to us, and where there are further studies, we're actually able to detect the effect of the galactic noise source, the center of our galactic noise source. That this peak of the noise at those higher frequency bands, sidereal peak, matches that of the Sagittarius A noise source at the center of the galaxy. And if we look across, one of the reasons we think this isn't associated with solar activity is that, in fact, we can see that the time of the peak does drift the 4 minutes per day that's associated with the movement of the Earth relative to on Saturdays, they turn on the fluorescent lights at KPH, and then all the data gets garbage because the fluorescent lights mess up. But if you look at the center here, you'll see that in fact this would be, if the sun were the source, you would expect to see the peak move across these 8 days would be directly horizontal, but it really does drift with the position of Sagittarius A. Anyway, these are the kinds of things you can do. We can get correlations with Clint's site over in Utah. We've done a number of such. There's much more. The data set exists. It's up there in the cloud. You can use Grafana to graph the data set that's in the influx database. The goal now is to increase the reliability and distribution and accuracy of the people who are contributing, the various sites that are contributing to this. There's, of course, an activity which is we need to calibrate the antennas. And that's another whole subject. Whoops. Okay. So I've rushed through this, and this is a rush through of a much larger set of data and measurements analysis. There's a 50-some page paper that Gwen has produced. So we welcome your interest, and we'll try to put this stuff up in a data set. If anyone is interested in looking in this data set, please contact me. It's all available to researchers, and we hope others will find it useful. And I hope to make this analysis technique utilize the personal weather station sites as well.
Absolutely. Thank you very much, Rob.
Okay.
Everybody hear me? KD2. All right. Now, which one is the laser? Right. All right, good morning, everybody. For what's left of it, my name is Gareth Perry. I'm from the New Jersey Institute of Technology. And I'm going to be describing today some Field Day 2019 operations related to the Swarm-E spacecraft, which is a spacecraft I've been working with for the past few years. I am KD2SAK. I'd like to acknowledge my co-authors here. Most of them also have their ham licenses, as you can see. And of course, the last two do not. I'd just like to point out, this is a HamSCI talk, so I've been with the HamSCI group, kind of got recruited or pushed into it by Nathaniel several years ago. I'd just like to point out the kind of collaborations that this thing has fostered. So, of course, I'm at New Jersey. I used to be at the University of Calgary in Canada. Nathaniel's now at Scranton, MIT Haystack. This was Johns Hopkins Applied Physics Laboratory, now over in private industry in Ohio. Steve Kepler's now at Clemson, Virginia Tech, and now I think Magda's at, I think it's Dartmouth. And then we got private industry, and then of course University of Calgary. And this is some of the collaborators I have through this HamSCI project. So it's really kind of ballooning and becoming a really fantastic producer of some great science. So I mentioned Swarm-E. That's the name of the spacecraft. It also has a couple of other names we give it. It's also known as Cassiope. This is the Cascade Small Sat and Ionospheric Polar Explorer. So this is the spacecraft here on the left, and then on Cassiope is EPOP. This is the Enhanced Polar Outflow Probe, and then this is a group of 8 instruments, kind of pointed at here. 5.5 are now working. So Cassiope was launched in 2013, September 2013, into a polar orbit, launched by Elon Musk with a Falcon when he was being nice to Earth observation satellites. That's kind of turned lately when he tried to run over the cryosat, but that's okay. The spacecraft operations for EPOP got taken over or extended by European Space Agency, so now it's called Swarm-E. kind of recast the name. But science objectives are to study energization processes in the Earth's ionosphere at very, very, very small scales. Okay, so actually, you should go back. 8 instruments, 5.5 are still working. And the instrument I'm going to be talking about here is RRI. This is the radio receiver instrument. It's 4 3-meter monopole antennas here. So, again, here's another shot of it. RRI, it's a digital radio receiver. It's used to study radio emissions, natural and artificial, so man-made, from 10 hertz all the way up to 18 megahertz. We do this over about a 30 kilohertz passband, and we sample at about 62.5 kilohertz. So we're looking at natural, artificial radio emissions. So we're talking about whistlers, what we call auroral hiss or auroral roar, and then in terms of artificial, radars, so over-the-horizon radars, these are radars that operate in high frequency range, and then of course HARP. So when Phil was talking about I don't have a knob to turn on and off the ionosphere, HARP is about the closest that we have to that. So we study HARP with this thing too. And really, like I said, study the HF radio wave propagation and study F-region density structures in the ionosphere. So this is structuring at about a 300-kilometer altitude in the ionosphere. Okay, so here's more of a schematic kind of showing the setup. We have a nice kind of graphic that I've used, and it was passed down to me, and it's been around since the proposal days of this spacecraft. So this is an altitude, and then this is just a distance along a great circle, and we have some sort of radar here blasting away some radio emissions, and the satellite moves over top, and it's measuring the radio waves it receives, and then it kind of moves over here, and all these radio waves are passing through aurora or whatever else is happening. And really, we're remote sensing the ionosphere by studying these radio waves to kind of give everybody a picture of what we're doing. So again, the altitude, we go all the way down to 350 or up to about 1,300 kilometers altitude for this spacecraft. So, the first experiment we did, the ham radio community, was a 2015 field day experiment. Of course, it was in June. I was at a meeting in Seattle, and I saw a talk by Nathaniel. We had known each other as grad students. I was just a new postdoc at the University of Calgary, and Nathaniel was giving this talk, essentially describing to the space physics community what became HamSCI, or really the infancy of HamSCI. And after the talk, I went up to Nathaniel and said, hey, that's a really great idea. I'm working with a satellite. We can tune into the ham band, or we can tune in, and maybe we could pick up some chatter, some HamSCI. I had no idea anything about ham. CW had no idea. Nathaniel looked at me and he goes, about 3 days from now is the 2015 field day. We should turn on for that. I said, sounds good. So I phoned, or I emailed over to the spacecraft operators. I said, how much time can we get? Are we going to be over North America during a time frame? And they said, yeah, we'll give you 2 minutes. Starting at 1:16 UT, you're going to be over here, and then you're going to go south for 2 minutes, and we'll shut you off. I said, perfect. So we tuned to 7.025 megahertz, got the data, and lo and behold, we saw something, which was super exciting. So this is essentially a waterfall plot. It's a spectrogram. So here's frequency here on vertical, and here's 2 minutes of time. This is ephemeris, so this is showing 1:16 UT to 1:18, and then here's our altitude. We were about 370 kilometers altitude. What you can see here, this is 7.025 megahertz, so this is in 40 meters, and this is 7.005. So frequency is ascending here. And what you can see is these little wisps of dark, and these are the CW signals. And a couple things we noticed, well, I've labeled these of the call signs, but one thing you should notice is we only see these signals for about the first 30, 40 seconds, and then we don't see it for the rest of the pass. So kind of keep that in mind as we go forward. So what we did is, well, first my jaw dropped. I couldn't believe it actually worked. It's just exciting being a postdoc and just kind of going, let's just try this and see what we get. So it worked. Then what we did was we went and decoded all those signals. So we tried some skimmers. A skimmer didn't work, so we had to orally, so by ear, decode it. Of course, I don't know Morse code. I didn't know then. I still don't know now. But Nathaniel and some others went to task, and they decoded, and we found several, but we could confirm 14, because of course it was field day. So what I had to do is email these folks and say, hi, we heard you with a satellite. Where were you on that night? You weren't at home. Give us your latitude and longitude. And in perfect ham radio fashion, I was getting these lats and longs down to about 7 decimals. I said, yeah, two is fine for me, okay. So that's what we found 4. We confirmed 14 of these, which was great. And the next thing we did was we put them on a map and kind of noticed that all these, so now this is the same map. This is North America. This is where we started our track and went south. And these blue little squares are where all these hams were located at the time. We had one that was way over on the East Coast. We did confirm we received this while we were kind of over the Chicago area, which is kind of neat. But most of them are clustered right over about the first 30 seconds of our path. So I mentioned this earlier. Why did those transmissions cut off after 30 seconds? We looked at RBN. Those folks were still transmitting. They were still tapping away. So something else was happening. And so we had to go and look at a ray tracer. So we went and looked at the HF ray tracer. And this is kind of a really spaghetti plot. But the top plot shows an altitude versus a latitude. So this is 45 degrees geographic latitude down to 35. And we have an altitude here that's about 350 degrees. And so moving right to left is the spacecraft track in these yellow boxes. And then I have kind of a contour plot showing the density of the ionosphere. And then what I did was I launched rays, HF rays, in a ray tracer from every one of those hams up towards the spacecraft. And you can see that only a few get through to the altitude. So what we were seeing, the reason why this cutoff happened is because of the ionosphere getting in the way. There was this iris of accessibility right over top of about Chicago where we saw all these hams. As the spacecraft moved south, it moved into an area where the critical frequency was just a bit higher and the elevation angles of these hams wasn't sufficient enough to actually pierce through the ionosphere, so they got internally reflected. So the exciting thing was we actually were able to pull out some plasma physics from this 2 minutes of data. And we actually pulled out quite a bit more. I just kept digging and digging and digging. We kept finding some other stuff. So at first, this was going to be a paper that started out as, hey, look at this. We saw some ham radio on CW. And then it turned into an actual plasma physics type of paper. So this was actually published in 2017 in the article in the journal Radio Science. So there's a bunch of the co-authors. So we can do, so from that 2 minutes of data, we can do some real science, which I thought was really, really exciting. So Nathaniel kind of pushed me into the HamSCI, and then when this happened, I got really interested in it, and a lot of my colleagues started to get interested. We did a couple more field days, and then the most recent one we did was 2019. So again, here's this kind of shot of North America, and in red and blue are some tracks of the spacecraft. Of course, thanks to the European Space Agency, we got a bit more money, which means we could do more downlinks with ground stations, which means we could take more data. So instead of getting 2 minutes of data, we got, well, these are all 8-minute tracks, so several 50 minutes, an hour of data over 2 days in 2019. So the red tracks are the evening tracks, and the blue tracks are the morning tracks during field day. And so you can see we started from northern Canada and went down to so we started about 50 degrees, 60 degrees north, went down to about 30 degrees north as we kept kind of going across the continent. And what we did was, for the morning tracks, we looked at 80 meters, and then for the evening tracks, or the afternoon tracks, we looked at 40 meters. So 80 meters was a bust. Here's a spectrogram, really. We didn't see much. We just saw a bunch of noise, I guess you could say. So anybody who wants to look at noise, we can look at this. So that's all we saw. But the 40-meter band was a lot more, 10 minutes, was a lot more exciting. So as you can see here, again, it's a spectrogram. It's a waterfall plot. We have the frequency of a dipole that we tuned on this, on RI, tuned to 7.025 megahertz, and here's our passband. This is seconds into our experiment, so this is 0 to 440 seconds, and we're starting at 57 degrees north, all the way down to about 33 degrees north. The difference between this and 2015 was that in 2015, we just kind of did it with a few days' notice. In the subsequent follow-up years, and especially 2019, we heavily advertised that we were doing this, just that we were listening in, and then just tell people about it. And so we always found that when we picked the right, and we got a bit better with picking when we would turn on. So instead of getting 14 maybe confirmed, we have just a dog's breakfast of everybody going on there. So you can just see it's just line after line of signal, which is really great. So this is what we saw. And if I just proceed forward, here's the next pass. So this is June 22nd at 20 UT, 2003 UT is when we turned on. This is the 22nd at 21:35. So again, the nice thing is you can see here is this is north, so 60 degrees north. So as we move south, you don't see much here. You see some noisy signals here, but then slowly when you get to about 57, 56 degrees, you start to see all the CW start to fade in as we're getting over the continental US or over the contiguous United States. And then there's just more of this. And again, more signal. This is 23 UT, so it's getting a bit later. And 19 UT on the 23rd. And this is 21 UT on the 23rd. So you can see some days are busier than the others. This is something that popped up. Before I even saw that we saw CW, this is something that popped up that really caught our attention. So if I scroll back through all these, it's a feature that is consistent. It's here on the edge, it's kind of here on the edge as well, it's right here again. And do not know what it is. So when that 2015 field day, when we had that fade out or when we had cutoff, everybody see all the CW nicely faded out. This one isn't doing that. You see CW, everybody's chattering away, then there's this huge whatever's happening, and then you see it come back in all the CW. So there's something there that's interfering. Doesn't seem to be noise, and it's repetitive. It's there pass after pass after pass, right? So we don't know what that is, and it's located consistently at about 37, 38 degrees geographic latitude. And Phil's thinking in the back there. I showed Phil this, and we think this is probably a geophysical signal of some sort, but we have to chase it down. Yep. Yeah, it's exciting when that happens. There's no idea what that is. No idea.
Is it a variety of longitudes?
No, it's variety of longitudes. So as the spacecraft track, actually I can go back. As the spacecraft moved west, it's kind of always stuck right about here, it seems to be. It seems to be some consistent feature.
It's not just the east coast of the US, or just the west coast?
No, it's there, yeah. So, yeah, don't know what it is. So, it's an exciting kind of, what is that thing? 5 minutes, what is that thing? So, and of course I haven't had time to go look at it, but you're just sitting there. Because now, of course, we're busy with lecturing and all that. Nathaniel knows that too. Okay, I just wanted to quickly point out, how do we process all that CW? In 2015, we just had to do a couple signals, so we had a couple of folks orally decode it. But with something like this, that gets a bit more intense. We thought about maybe writing our own skimmer, but Nathaniel said that's probably more difficult. So what we decided to come up with was what we called the Golden Ears Project. And this comes from Phil, this kind of name. Instead of writing an own skimmer, we just thought to work smart, not hard. So what we decided to do is just take all that data and just channelize that passband into 500 hertz chunks, record that data, just put it to a WAV file, and rely on the generosity of CW operators with golden ears to tell us who is there. So we started that, initially started that, and we've done a first pass at things. So this is an example of what we're doing. Here's our band. Here's at 40 meters at 7.025 from that 2019 field day. And we just take a little small pass band. We put it over to an audio file, and I'll see if this plays. Is it going to play? Can anybody hear it? Do I have to do the microphone thing? Hopefully you hear it. Give it a second. You know what I bet it didn't do? I put this on Keynote, and I trimmed it to about 5 minutes into it, but when I went to PowerPoint, it probably didn't trim it. So I'm not going to keep people here for 6 minutes to listen to a bunch of noise until this cuts in. But what you would hear is a bunch of about 5.5 minutes into this, and I have all these files, and I can share them with everybody, of course. You start hearing people chattering with one another, and it's actually really nice and clear, surprisingly clear. So to summarize, the exciting thing from my perspective, I come from a science background, not so much a ham background, is that we can do radio science using ham transmissions as an HF source, so as a signal of opportunity. And we're doing large-scale radio propagation experiments, and not for fun, right? We're not just saying, hey, we can see some CW seeking. We can actually do some genuine bread and meat and potato space physics with this. So HAMS, and I keep telling this to people in the science community, that they're a great resource and an ally for solar terrestrial physics. And we got a lot of work ahead of us to, as I said, develop a more efficient way of decoding ham transmissions. Maybe we can write our own skimmer, and to actually validate this participation of this large group when we do stuff like field day and other kind of DX contests, to use that as a signal of opportunity to do these HF ray tracing studies. So more operations with HAMS is what we're planning and all the time. And so these sound files I just mentioned with the Golden Years project, I'm going to process them and kind of make them available so anybody with anything that plays a wave file can go in and listen and maybe write down who they hear, and then we'll have something to upload so people can let us know and we can do some more science with that. So I'll leave it at that. So everybody can go eat lunch.
Okay, any quick questions? Right here.
Why did you work in the CW portion of band? Why not FT8? There's a lot of FT8 during field day, and you would have had the computer decoding and all kinds of extra information.
Yeah, 2015, I didn't know about that. 2019, I think there was a bit of talk about that, but we hadn't done that. So it's something we could do in the future. Phil, did you want to add to that?
I'm just going to add one comment. FT8 is a spread spectrum kind of transmission. It's not spread that.
Ah, there you go.
So the ionosphere is dispersive. So when it goes trans-ionospheric, there's no guarantee that all those phase fronts are going to necessarily line up. So we have to crawl before we can walk. A carrier tone that is essentially unmodulated for the time that the key is down is a lot easier to deal with first.
Yeah.
When you get your feet wet on that, then you can try the FT8 decoding, because there's a whole bunch of extra information in that.
And that's one of the reasons why the skimmer wasn't working, was because there was too much flutter on the actual signals, because the ionosphere was really messing with those pulses. Yes?
Yeah. Are you limited to 80 and 40, or could you try other bands as well?
We only tried those bands, but we could try anything we wanted.
I'm
really.
thinking 80 meters during the daytime on field day is not going to have that much
Right,
activity.
and we have 4 years of data to show that, actually. But RRI can tune from 10 hertz all the way up to 18 megahertz, so we can pick and choose, really.
Okay, thank you very much.
Good.